All right, let's talk about the art of chemical control. We're going to dive into how chemists can basically act like sculptors with their solutions, precisely deciding what dissolves away and what crashes out as a solid. So picture this. You've got this complex chemical soup, a whole mix of different things all dissolved together. How in the world can you reach in and pull out just one specific ingredient and leave everything else behind? Well, that's the puzzle we're going to solve today. To even start tackling that problem, we need to understand the rules of the game. And in the world of solubility, the most important rule is a little something called the solubility product constant, or KPS for short. Think of the KSPS as a hard and fast saturation limit. It's a number that tells you the absolute max amount of a compound that can possibly dissolve. If you try to add even one more grain, the solution basically says, nope, I'm full, and that extra stuff just stays solid. So a really, really small KSPS value, that's a huge red flag that a compound just does not want to dissolve. Okay, let's make this real with our first example. Silver chloride, AgCl. Chemists call this a sparingly soluble salt, which is a fancy way of saying it's pretty stubborn. When you drop it in water, most of it just sits at the bottom as a white powder. But a tiny, tiny fraction of it does break apart into silver and chloride ions. So how do we figure out exactly how much dissolves? We use the KSPS expression. As you see in step 1, it's just the concentration of the silver ions times the concentration of the chloride ions. Now, since every one AgCl molecule gives us one of each ion, their concentrations have to be equal. We'll just call that unknown amount x. This makes our math way easier. KSP equals x squared. All that's left is to plug in the known KSP value for AgCl and solve for x. And there's our number, 1.34 times 10 to the minus 5 molar. Let me tell you, that is an incredibly small number. It just confirms what we already suspected. In pure water, silver chloride is mostly insoluble. This is our baseline. Now, let's start messing with it. This brings us to our first tool of control, the common ion effect. What happens if we try to dissolve our silver chloride, not in pure water, but in a solution that's already got one of those ions floating around? The secret here is a fundamental idea in chemistry called Le Chatelier's principle. And all it really says is that chemical reactions like to be in balance. If you mess with one side of the reaction, the whole thing will shift to undo what you just did. Since our dissolved ions are a product, if we add more of that product from an outside source, the reaction pushes back by making more of the reactant, which, in this case, is our solid salt. Let's just compare these side by side. In pure water, on the left, it's a totally open playing field. But on the right, in a sodium chloride solution, the water's already loaded up with chloride ions. That kid's saturation limit we talked about, it gets hit way, way faster, leaving way less room, so to speak, for our AgCl to dissolve at all. Let's look at the math again. The KSPS expression itself doesn't change. But this time, that chloride concentration isn't just X anymore. It's X from our AgCl plus the 0.1 molar that was already in the water. Now here's a nifty little chemist trick. We know from our first calculation that X is going to be microscopic compared to 0.1. So we can just approximate and say that X plus 0.1 is, well, it's basically just 0.1. This makes solving for our new X super simple. And would you look at that result? 1.8 times 10 to the minus 9 molar. Let's compare that. We went from 10 to the minus 5 down to 10 to the minus 9. That's a 10,000-fold decrease in solubility. We just took a salt that was already barely soluble and made it almost completely insoluble. Now that is control. Okay, so we've learned how to stop something from dissolving. But what if we want to do the exact opposite? How can we take a solid that's already sitting there and force it to dissolve completely? For this next challenge, our target is iron 2 sulfide, or FeS. Just like our silver chloride, it has a tiny KSP, so it would much rather be a solid. Our mission is to take that solid and, on command, make it vanish back into the liquid. Here's the game plan. Our solid FeS is in this delicate balance with its dissolved ions. But when we add a strong acid, those hydrogen ions act like little magnets for the sulfide ions. They snatch them up and react with them, pulling them completely out of the solution as hydrogen sulfide gas. And what does Le Chatelier's principle tell us? We've just removed a product, so the reaction has to shift to the right to try and replace it. And the only way it can do that is by dissolving more of the solid FeS. So the big takeaway here is that pH is way more than just a measure of acidity. It's a powerful lever.
By changing the pH up or down, we can directly control the concentration of certain ions. And when we do that, we can basically turn the solubility of a compound on or off like a light switch.
All right, on to our final and most precise tool. We've gone from stopping something from dissolving to forcing it to dissolve. Now, let's get surgical. Can we actually pull just one specific ion out of a mixture that has two very similar ones? Here's the setup. We have a solution with both chloride and bromide ions floating around. Chemically, they're super similar. The goal is to add silver ions and selectively crash out the bromide as solid silver bromide, while leaving all of the chloride ions still swimming in the solution. How is this even possible? Well, we just have to look at our rule book, the KSP values. Check this out. The KSP for silver bromide is almost 1,000 times smaller than for silver chloride. That's our key. That smaller KSP means it's way, way less soluble, so it's going to hit its saturation point and precipitate out as a solid long before the silver chloride even thinks about it. The trick is that we have to add our silver ions slowly, drop by drop. A precipitate will only start to form at the exact moment the concentrations of the ions, multiplied together, hit that magic KSPS number. And here it is, the aha moment. Just look at the insane difference in the silver concentration we need. It takes just a whisper of silver to get the bromide to start precipitating. But to get the chloride to even start forming a solid, we need a concentration over 200 times higher. This gives us a massive window to work in. So by adding just enough silver to stay within that window, we can pull pretty much 100% of the bromide out of the solution as a solid, all while the chloride ions are left completely untouched. That is some serious, high-precision chemical separation. All right, let's recap. Let's take a look at the awesome chemical toolkit we've just put together. We've really built a powerful set of tools here. First, we have the common ion effect, which is our go-to for making things less soluble. Then we have pH control, our clever method for making things more soluble by yanking an ion right out of the system. And finally, selective precipitation, our high-precision technique for separating ions just by taking advantage of their different KSP values. And here's the thing, this isn't just theory in a textbook. These very principles are at work all around us, from the slow, patient process of stalactites forming in a cave to the high-tech industrial purification of life-saving medicines. Understanding this stuff, understanding chemical equilibrium, gives us the power to manipulate the world around us, which really just leaves one question. What are we going to learn to control next?